Have you ever stopped to wonder how a robot knows exactly where it is? I mean, really think about it. Down to the millimeter, second by second. It's a huge challenge, especially when the world is just this constant stream of noisy, messy, imperfect information. Well, today we're going to unpack the surprisingly elegant mathematical tool that turns all that chaos into confident, precise navigation. I mean, think about it for a second. What happens when a self-driving car goes into a tunnel and loses that GPS signal? Or what about an underwater drone that, has no signal to begin with? How do they keep track of where they are? They obviously can't just rely on one single source of truth. So here's the secret. It's not about having perfect sensors, because perfect sensors don't exist. It's about being really, really smart at fusing together multiple sources of imperfect information. It's this constant dance of guessing, checking, and then correcting over and over again. And the absolute heart of this process is about mathematically understanding and managing uncertainty itself. Okay, so here's our game plan for this explainer. First, we're going to get inside a robot's head, so to speak, to see how it thinks about its own location. Then, we'll look at the simple two-step dance it's constantly doing to navigate. After that, we'll meet the famous Kalman Filter, find its one big weakness, and then, this is the cool part, we'll reveal the clever trick that makes it all work in the real world. And you're going to want to stick around because we'll show you why this stuff matters in your everyday life in ways you probably don't even realize. All right, let's jump in. First up, the guessing game. So for a robot to navigate, it needs something called a belief, which is just its best guess of where it is. But here's the key. It's never 100% sure. So that belief isn't just a single tiny dot on a map. It's fuzzier than that.
Instead of a dot, the robot represents its location as a Gaussian distribution. You've definitely seen this before. It's the classic bell curve. And what's so great about this is that it's super efficient. You only need two numbers to describe the whole thing. The mean, which is the robot's best guess, and the variance, which is just a number that represents how uncertain it is about that guess.
And this gives us a fantastic way to visualize confidence. The very peak of that bell curve, that's the robot's most likely position. But the width of the curve, that's its uncertainty. So a tall, skinny curve basically means the robot is thinking, I'm really, really confident I'm right here. But a short, wide curve, that's the robot saying, I'm pretty sure I'm somewhere in this general area. So the big question is, how does the robot update this belief? How does it get more certain over time? Well, it uses this simple but incredibly powerful two-step loop over and over and over again. This is the fundamental rhythm, the heartbeat of all modern navigation. Predict, then update. Predict, then update. It just keeps on repeating. So first up is the prediction step. The robot basically says, okay, based on how fast I was going and in what direction, I predict that in the next fraction of a second, I'll be right over here. But of course, this is just a guess. Wheels can slip, underwater currents can push it off course, and because it's just an estimate, the robot actually becomes less sure of its exact position. Visually, our bell curve gets wider and a little flatter. But then comes the update. This is the aha moment. The robot uses a sensor. Maybe it's a sonar pinging off a landmark, maybe it's a camera seeing a wall, and it gets a real measurement from the world. This new piece of information lets it correct its earlier prediction. It fuses the prediction with the real-world measurement, and by doing that, it becomes more confident. Our bell curve suddenly gets taller and much narrower. Now, this whole predict-update process has a name, and it's honestly one of the most important algorithms ever developed in the 20th century. This is the Kalman Filter. It's a set of mathematical equations that gives you the best possible guess of where something is by combining a prediction with a noisy measurement. And when I say best possible, I mean it in a very specific mathematical sense, perfect. The secret sauce inside this thing is a value called the Kalman gain. The easiest way to think about it is like a dynamic trust dial. If the robot sensors are super reliable and accurate, the gain will be high. That tells the filter, hey, trust this new measurement a lot. But if the sensors are known to be noisy and unreliable, the gain will be low, which tells the filter, you know what, stick closer to your own prediction, it's probably better. So here's the crucial point. The Kalman filter is mathematically proven to be optimal. It gives you the best possible answer you can get. But, and this is a huge but, it's only perfect under one very specific condition. The system you're tracking has to be linear. That just means all the relationships are simple, predictable, straight lines. You double the input, you double the output. And that's a problem. And that brings us to the big, messy complication. Because that clean, predictable world of straight lines, well, it's not the world that our robots actually live in. The reality is, pretty much any robotic system you can think of is nonlinear. Things don't just move in perfect straight lines. They rotate, they turn, they accelerate. The relationships are complex and full of curves. This slide really says it all. The standard Kalman filter, it's built for that simple, predictable, linear world on the left. But a robot turning a corner? That involves trigonometry, sines and cosines. That's the complex, curvy world on the right. And when you try to jam a nonlinear reality through a linear filter, well, your perfect estimates suddenly fall apart, fast. So, what do? How do we fix this? How can we possibly use our perfect tool for straight lines in a world that's full of curves? Well, it turns out we use a very, very clever trick. The solution is a modified version called the Extended Kalman Filter, or just EKF for short. And this thing is the absolute workhorse of modern navigation for this exact reason. The EKF's big trick is something called linearization, and it's brilliant. The filter knows it can't handle the entire complex curve, so it doesn't even try. Instead, at every single time step, it just looks at its current best guess on that curve and says, you know what? Right at this exact point, for this tiny instant, I'm just going to pretend this curve is a straight line. It makes a simple local approximation and moves on. And here's the truly beautiful part of the whole thing. To predict where it's actually going, its position, the EKF uses the real curvy nonlinear model. It uses the best, most accurate physics it has. But to predict how its uncertainty is going to change, how that bell curve should stretch or shrink, it uses that simple straight line approximation. So it gets the accuracy of the complex model with the computational simplicity of the linear one. It is literally the best of both worlds. Okay, I know this might sound like a bunch of abstract math, but this process, this ability to make a smart guess in an uncertain, curvy world, it's running silently in the background of our modern lives all the time. You know that little blue dot on your phone's map that seems so smooth? Yep, it's using an EKF to fuse the noisy GPS signal with your phone's motion sensors. Drones use it to stay perfectly stable in the air. Self-driving cars use it to track every other car on the road. It is absolutely essential for navigating everything from deep-sea research subs all the way to spacecraft docking with the International Space Station. The core idea here is just so powerful. You take a prediction, you take a measurement, and you blend them together intelligently to find the truth that's hidden inside all the noise. The world is, by its very nature, uncertain, but with the right tools, we can navigate it with confidence. So it makes you think, doesn't it? What problem out there would you solve if you could just make a really, really smart guess?